Hello, everybody. Thank you for attending a research and innovation conference and listening to this talk. So today I will talk about the ductility issue in titanium alloy, and where is mainly in its application exposed to very high temperature in air or other atmospheric condition. And I will talk about the microstructural parameters that affect that ductility in titanium alloy. So myself, I'm Soran Birosca from School of Mechanical and Design Engineering. And I did this work with my postdoc, Peter Davis, when I was in Swansea University. And today, just to give you a little bit of background about my research activity, for the past, let me get my pen for because I get used to use the pen when I'm giving a talk. Now, for the past 15 years, I've been working on the materials used in jet engine, mainly. For example, I work on the materials used for the blade bar in the jet engine, which is titanium 64. And this material is exposed to temperature. Maximum temperature can be exposed is about 450, or they said 500, but we wanted to be below that operation condition for safety issue. And also I work on titanium 62 for the titanium used in the compressor side for the disc and also the blade. And I spent so many years working on nickel-based superalloy, which is used at turbine side, single crystalline, also polycrystalline, like RR on southern use for the jet engine, for the disc application, and so on, which is, we call it hot side. So this is a very, very hot part of the jet engine. This is very, very cold part, not very cold, relatively cold, about below 500. That's what we call it. Called the jet engine. If you look at the titanium, is part of made in blades and discs are 40% of them are made in titanium. 30% is 40% is in nickel, and 30% is titanium. I also work on the steel shaft, which is in the core of the jet engine, which is 25% of the materials used in the jet engine are actually. Now, I'm just talking about the jet engine. If you talk about the airframe, you have a composite, 50% of it, and also you have titanium as well, because it's light alloy. And to increase the thrust of the jet engine, they used a very, very light alloy like titanium, which is again 50% of the airframe, and 30%, and now even more than 30% of the jet engine. And of course, aluminum is a very good candidate for the light alloy. However, it doesn't have the strength to be used in the jet engine. Now, today, I'm not talking about the blades, or I'm not talking about the disc. I will talk about the casing today, where you have the compressor casing is made of titanium alloy, because it is very hot environment, so you have to resist the and not preventing the heat transfer from the jet engine to outside world. And so I'll talk about this part where it should be manufactured and have got a lot of ductility to absorb the energy during the impact. Now, just to give you a background about this work, so this is a compressor casing here. So where you put the compressor inside the blade and disc, you put within which stand on the shaft, you put it inside the jet engine. And now this is a casing for intermediate compressor casing, because for the compressor you have a high pressure compressor, low pressure compressor, and intermediate pressure compressor. So the materials used nowadays is mainly titanium 6242S. Now, this material has got a temperature capability of 450. And because we wanted the jet engine to be bigger, lighter, and so you need to absorb more air, to suck more air in the engine. So you need bigger engine, you need a hotter engine, but you need a light engine. That's why we're using titanium. And so the objective for the near future is to increase the materials capability by 50%. So that's 450, it should be around 500. Now, within this study, we look at it, we were looking at the other candidate, which is titanium 84. Is it actual replacement for titanium 6242S to be replaced, and if the materials functioning better? So now the main issue for titanium alloy to be used in this large part is a ductility issue, and that's what we were focusing on. Now here, if you look at it, if you look at the chemical composition differences between the two titanium alloy used in this study is very, very small. For example, aluminum kind of similar, but we increased the tin to 4% from nearly 2%, which is quite a lot. And then we reduced zirconium, which is silicide former, press plate former, a little bit, and molybdenum we increased it a little bit, and we put niobium here, right? And silicon we reduced it a little bit. So I will tell you about why we reduced silicon in this study. Now, the titanium was made through centrifugal casting, and that's done in Doncaster company in the UK. And other part is being forged, ring roll forged by Forgital Group in Italy. So basically, I don't want to go through the details of this processing. However, for the centrifugal casting, you pour it just briefly. You pour the molten alloy into a molten, from the ladle, you pour it on the basin, then you throw it to the rotating mold, which is rotated by the motor, and then it will be stacked on the mold wall, and then it will be solidified during the cooling. And this is what we call a centrifugally casted. And then we did a lot of heat treatment and also age to maximize the property of this alloy. And from the Forgital Group spa in Italy, they ring roll it, where they normally use this technique for making this type of, or even for the car wheels, they are using the same technique. So you put pressure on the two ends of the titanium on both sides here and there, and then you are using the two pin to put pressure on it to thin the material. Of course, after that you heat treat it, an extensive heat treatment, and also age it to optimize the property for this alloy. Now let's see what's happened. So what we did, we made this alloy. So what we had to test them at very high temperature for a long time of exposure, same as these casing are actually used in jet engine. So it was very, very clear from the test that actually when we had no exposure at all, which is the blue one, this is centrifugal cast titanium 834, the ductility was about 11%, which is a little bit lower than as we will discuss later. And then when we expose it to high temperature, we expose it to high temperature at 500 degrees, that's the temperature we want these materials to operate and to be used. For 100 hours, we use the ductility is reduced dramatically. And when we expose it at 500 degrees Celsius, the ductility is again reduced after 200 hours. But after 500 hours, no ductility whatsoever. The materials after elastic form is just collapsed. It just failed. And so huge reduction in ductility with increasing exposure time at 500 degrees Celsius. And that was not very good. So we want to understand what's happened. When you look at the forged material received from Forgital Group in Italy, we saw the ductility even with the UTS and also the yield stress was a little bit higher than centrifugally cast titanium alloy, but also the ductility is much higher, is about 19 strain percent. And even when we expose it at very high temperature for 100 hours, for 200 hours, for 500 hours, still remain the same. So no reduction in ductility with increasing exposure time, which is fantastic news. However, Forging, we in the modern world, we want to avoid it because when you're adding more materials to the alloy, forging has become more difficult. That's why people will go from graphite casting to the centrifugal casting and so on. Now, let's see why that happened. What's the difference between the microstructure? Well, the microstructure of the centrifugal cast, as we see it here, is a typical, what we call it, Woodman-Statten microstructure, which is a colony lamellar microstructure where you have a very large prior beta grain, and then these small lamellar microstructure. So when you expose it to high temperature, what's happened? You increase slightly the width of the material. However, this is not very good or ideal microstructure for crack propagation, for deformation, for ductility. Because when we did some Ebsd work here, if you look at it, this map is Ebsd work where you're looking at the orientation, crystallographic orientation of the individual grain within the alloy. You'll see when you look at the misorientation here, the misorientation is very, very minimal. It's below 2:1. What that means? That means there is little orientation differences within the lamellar structure. So if you have a crack, the crack is go straight away, go without any facing any restriction or any obstacle through the crack propagation. And that's so the plastic deformation on this part is very easy. It's very easy to activate the slip system activation and the crack propagation through this microstructure. That's why the lamellar microstructure, or what we call it colony Woodman-Statten microstructure, is not good for some if you subject it to tensile and fatigue property. While the forged alloy, which is produced by ring roll forging, it consists of biomodel microstructure, where you have equiax alpha grain, and in the middle you have what which is we call it biomodel microstructure, primary alpha and then transform beta in between, which you have very strong alpha here and then very neat type of secondary alpha in between, and that's what restricting the dislocation to go through, or the crack formation or slip transformation is restricted, and also make obstacle for them to pass through neighboring grain, and that's makes the materials much stronger. Now, if we look at this part, we did some 3D Ebsd. So what we did, we grinded and polished the materials, and we look at the crack, how the crack is actually going through the material. And in fact, we were right, because from the surface, we go deep inside the material. We found out the crack is easily can go through the material and the crack initiation is actually, we found it is actually in the triple point. That's what we call a triple junction between the grain, where a few grain they met, and that's a weakest point. So the crack is initiated between the prior beta triple point, and then easily could go through the lamellar microstructure, because they have very, very similar orientation, not any obstacle, not any restriction, so the crack can go very easily. So from that, we found out that the cast microstructure and forged alloy microstructure is actually responsible for 7.2% of the ductility in the cast microstructure when we compare even without the exposure. Now, we realized the microstructure differences is responsible for 0.1 percentage strain of the ductility regression between the two. What about the rest? Because that's why we went further, and we looked at the so what we did, we tested with removing what we call it alpha case. So what's happened, these cases, there is always an outside layer, which is we call it alpha case. Alpha case, because if you expose it at temperature, so the oxygen will absorb to the metal, and it will transform the first layer of all the beta to alpha. Alpha phase in titanium is a little bit harder. So we remove that layer to see the effect of that layer, and we expose it to 500 again with the oxide base being removed, alpha case being removed, and we tested against same condition. And we realize actually there is a proportion ductility lost after exposure. So that means the alpha case layer was responsible for about 5% reduced to 1%. So that was approximately 30% of the reduction was because of the alpha case. Now we wanted to go further. So now we get some part of this. That's why we wanted to quantitatively look at this part. We said the alpha case is responsible for 3.6% of the reduction of the ductility. And now we wanted to know what about this one. So what we know there are so many precipitate in the alloy. We want to know which one is more effective for reducing the ductility in this alloy. We have, for example, the carbide, which will be dissolved around after 570 or something around that. So if you heat treat it and then quench it, you're removing the carbide. You can assess in the same condition. You can assess what effect of the carbide is. And then you have the alpha case, alpha 2, we have alpha 2, which is very brittle and order stretching to metallic, and it will dissolve at 675. So we heated the material at 800 and then quench it to remove all the alpha 2. We did that for the side as well, right? So silicide is very hard, brittle precipitate in the titanium alloy. And what we did, the solvent temperature for silicide is about 1050 degrees Celsius. So what we did, we heat up the material, heat treated at 800 to remove the alpha 2, and heat treated at 1000 and to remove the alpha case. And what we found out actually after we made the alpha 2 smaller to be less effective for the ductility issue and also for the silicide, we found out it is very little effect of the alpha 2, but silicide have got huge effect on the reduction of the ductility. 4.4% of the ductility recovered after we removing the oxide. And we want to understand why. So I'll just briefly show you before the end how it has been done. So when you look at the cast materials prior to high temperature exposure, these silicide was small in size and they were on the alpha phase. And when we expose it 500 for 500 hours, at 500 degrees Celsius, we see these kind of silicide are coarsened. They become bigger. They become a void around around them with the beta and alpha phase. And that void formation is very, very critical because that's a very bad and weak point for initiating crack, and also the crack will propagate dramatically from there. Then we want to understand what's going on this part. Why on the alpha phase we did high resolution EDX. Now, this is the beta phase. We found out there is the titanium alloy here on the beta phase was lower in titanium, lower in aluminum, which is a very strengthening element, but very high concentration of zirconium, which make it a very, very good area for the precipitation silicide, and that what causing a problem. And then we did some very detailed line scan EDX. So we found out is actually by the time when the aluminum, the red line here, reach starting from alpha 2 to beta phase, the aluminum is reducing in its concentration and minimum at on the beta phase. So this is beta and the rest is alpha. So that's a depletion of aluminum made this part or region weaker than the rest. So that's why crack will be initiated around the silicide much faster and go through the materials to fracture it. And also that's the same case in titanium. However, it has very high niobium and molybdenum, which is made suitable site for the silicide formation. So in conclusion, because my 20 minutes is finished and I hope it was useful, so we quantitatively we look at the microstructural parameter individually and what the hierarchy system is affecting the failure or the ductility of the material. And in conclusion, we found out the original microstructure within the forged and centrifugally cast is responsible for around 7% of reducing the ductility in the material. Around 4.4% is silicide was responsible for reducing that proportion of the ductility. Alpha case is very powerful, is responsible for 3.6, and alpha 2 has got limited effect on the reducing the ductility by 0.2%. And we have 1.4 which is we didn't figure out what is it, and I will leave that for you to study further on that aspect, which is very, very interesting aspect for looking at the materials used in jet engine. If you need more information about this, you please go to, we published this paper in Acta Materialia, and the citation is there, and also in one conference in San Diego. So I hope it was useful, and have a great day. Thank you very much for listening, and we'll see you. Hopefully you will enjoy the rest of the day. Thank you. Bye-bye.